Okay, let's have a look at a little bit more practice about working out the units of Kc. So let's look at this first reaction here. We've got methane. Oh, no, I haven't. The first reaction we've got is ammonia, the formation of ammonia. Okay, so we've got nitrogen, hydrogen forming ammonia in the Haber process. You're probably pretty familiar with that. So 2 should be up at the top there. Squared. So don't forget, yeah, it's these big numbers in front that become the stoichiometric coefficients, as they're properly called, become these indices here. So what does that mean? We're going to have this one, then it's going to be moles per decimeters cubed on the top, squared over, now that's mole per decimeter cubed multiplied, and this is, you're going to cube this one, and this one is to the power of 1. So that means we're going to have mole decimeter cubed to the power of 4 altogether there. So that means we can cancel, do a bit of cancelling out there. We can get rid of those. 2 of those will cancel out, and that will give you 1 over that. So simplify that, that's going to be 1 over mole squared dm to the minus 6. And how do we bring it all onto the top line? We change the sign. So the units there are going to be mole to the minus 2 dm to the plus 6. That one. Okay, let's do this one here. Methane reacting with steam. Okay, this is really important. This is how they make hydrogen for the Haber process and for various other industrial uses. It's made from methane. Right, so we're going to have there, there's going to be, we've got that to the power of 1, that's the power of 3, so it's going to be mole dm to the minus 3 to the power of 4. And on the bottom we've got, well, that's the power of 1, that's the power of 1, so we've got mole dm to the minus 3 squared. Okay, so they will go all together. And that 4 is going to become a 2. So that's going to be mole squared dm to the minus 6 is the units of that one. Okay, we'll do this one here, sulphur dioxide. This is in the contact process. So sulphur dioxide reacts with SO2 to make sulphur trioxide, which is then used to, sulphur trioxide is used to make sulfuric acid. So we're going to have mole dm to the minus 3 squared on the top. We've got to the power of 2 and to the power of 1 on the bottom, so that's going to be mole dm to minus 3 to the power of 3. Cancel those out, so that goes from the top, and that 3 turns into just a 1. So we've got 1 over that, and so that's going to be mole to the minus 1 dm to the plus 3. Okay, now this one is an interesting one. Let me see where I've included this. Right, on the top we've got mole dm to the minus 3 squared, and we've got a power of 1 and a power of 1, so that one on the bottom is also mole dm to the minus 3 squared. Okay, so that means they're both going to cancel out, aren't they, with each other? So there are no units. If you like, there Kc is a ratio, with no units, and it's easy to spot these sort of equations. Where you have no units, it's when they've got the same number of moles on both sides. On both sides that happens. Okay. We'll see that makes calculations a bit easier sometimes when you have that in the next few videos, and they quite often ask questions where you do have this same number of moles on both sides, because it makes the calculations a little bit more straightforward, and sometimes you wouldn't be able to do them if you had different number of moles on either side. Another one of those, if you have done this in organic chemistry, is Ester Formation. You have the same moles. So Ester Formation, you get a carboxylic acid. So let's see, that's ethanoic acid, and you react it with an alcohol, say ethanol, and you're going to form the ester. Make a bit of room. So the ester is and you form water as well. That ester would be called ethyl ethanoate. And you can see this one would have no units because on the left-hand side, we've got 2 moles, we've got an ethanoic acid and an ethanol. And on the right-hand side, we've got 2 moles, we've got an ester and water. So that's another one of these. Now, whenever you state a value of Kc, it's meaningless to talk about Kc unless you state the equation. There's no good saying the Kc for the formation of ammonia. And we'll see, for example, we'll see why. Right. Let's take this example, this one as an example. Now it's an equilibrium reaction. So one person may write it down as H2 plus I2 goes to 2HI. And Kc there would be equal to HI squared over H2 times I2. But because it goes backwards, there's nothing to stop somebody else from writing it this way around. They could write 2HI and have that as decomposing into H2 and I2. In that case, Kc, let's call it Kc dash, would be equal to H2 concentration of I2 over Hi. Now, what is the relationship between, what is the relationship between this Kc, the green one, and the red one? Well, you can probably see that all you're doing is turning this fraction upside down. So it's the reciprocal. So in that case, Kc would be equal to 1 over Kc dashed. And they've asked that question a few times. They give you a value of the green Kc, say it's like 60.0, and it wouldn't have any units with it. Let's say that the green Kc is equal to 60.0. I'm just making the number up. So the red Kc would be equal to the reciprocal of that, which is red Kc would be equal to 0.0167. No units for that one. And another case where you might have something strange there is I'll just let's think about the SO2. I'll just clear that. Let's think about the SO2 reaction. Now, some people might write it 2SO2 plus O2 goes to SO3. But equally, somebody else may balance it like this. They might write SO2 plus a half O2 is equal to SO3. So let's write the equilibrium constant down. So this Kc is SO3 squared over SO2 squared times O2, whereas this one, well, Kc there is going to be equal to SO3 to the power of 1, SO2 to the power of 1, concentration of oxygen to the power of a half. And don't forget, the concentration of anything to the power of a half is equal to the square root of it. If you remember your rules. And this is, so what's the relationship between this Kc and that Kc? Well, Kc is equal to the blue Kc squared. So, you know, if they ask you to, they give you a value for the blue KC of 4, then the value of the green one would be 16. And the units are going to change as well. Now, the units for this one, we worked them out before. The units for the black one is mole to the minus 1. Sorry, mole to the plus 1. dm. Sorry, mole to the minus 1, dm to the 3. Whereas, let's have a look at the blue one. Well, that's going to be a bit more complicated. The units of the blue one, this one here, let's do it. It's going to be moles per decimeter cubed for the sulphur trioxide over the moles per decimeter cubed for the sulphur dioxide. Now, remember that this is the power of half is the square root of something. So the units of that are going to be mole to the half dm. Well, it should be dm to the minus 3. We're going to divide by 2, so that's going to become dm to the minus 3 over 2. So do a bit of cancelling out. Those two cancel out, don't they? So the units are 1 over mole to the half. So put it onto the top line, that gives you mole to the minus half dm to the plus 3 over 2. So very strange units there indeed. Okay. Right. Now let's have a think what Le Chatelier would say about all of this. Okay. What would he say? Well, let's have a look at let's have the hydrogen and the iodine one. Okay, we've got hydrogen and iodide. And that's 2Hi. Okay. Right. So saying if we've got a box, okay, and in there we've got H2, I2, and we've got Hi, mixture of all three gases, and it's at equilibrium. And let's say we've got a value of Kc. I'm just going to make a number up. Let's say it's 5.0. Okay, so the Kc is always got to be the same number. Now, if you come along and you introduce a little bit more of hydrogen into there, well, that's what we know. Le Chatelier will tell us if you introduce more of that, it would try and undo the change. So what would happen is the equilibrium position would move to the right to try and destroy the H2, do the opposite of what you tried to do. Let's write down the expression for Kc there. Kc is equal to Hi squared over H2, I2. Okay, so we've got to keep Kc the same. So if we add more H2 to keep, say, Kc the same, obviously we've got to get more of this. So that means the equilibrium must move to the right. Okay, so that's just a little bit about units. How you have to be careful which way you must state the equation, because that will affect the expression for Kc, and express the units for it. And then just a little bit of explanation about how that fits in with what we know about Le Chatelier's principle.